Let's have one more example. So this example says we have a gas flows through an adiabatic nozzle at steady state. Oops. So here we have adiabatic nozzle at steady state, entering at 0.5 megapascal at 675 Kelvin and leaving at 0.1 megapascal, assuming the nozzle is reversible. What is the temperature of the exiting gas, assuming the gas has an ideal heat capacity 40 joule per mole Kelvin? Again, here he is telling you that this is not an ideal gas, but the ideal gas heat capacity, so the heat capacity that you need to use in this step M2, he give you the value of Cp at this step, okay? Because at the last point, if you know that, he gave you an equation of a state to use, which is different from the ideal gas, and he gave you the value of parameter A in the equation for this one, okay? So don't get confused of this one here. So when he says we have ideal gas heat capacity, so this one, so this is for step number 2. For step number 2. Calculations. And doesn't mean we have ideal gas. Okay. Okay. So here in this example we have nozzle. He says we have reversible nozzle, we have adiabatic nozzle. If you remember from the previous chapter of the cycles, if you have something reversible, adiabatic, so these two words, we replaced them before by something called isentropic. And isentropic means the change in the entropy was equivalent to 0. So only from these two words, so reversible adiabatic, this is equivalent to isentropic. Isentropic means there is no change in the entropy. Okay, so in order to find this one, this will be the equation that you will use. That we know that reversible adiabatic means that there is no change in entropy. Okay. So this is what we will find. So delta S, the molar change of the entropy, if we use this equation, so it will be delta S1 plus delta S2 plus delta S3. Again, delta S1, this will be negative S1 residual plus delta S of ideal gas plus S3 residual. So this is the equation here. Delta S1 negative S residual, delta S3 will be S residual, delta S2 is delta S of ideal gas. And we know that the result of all of this answer, this will be 0, because delta S is 0 in this one. And then let's start with delta S of ideal gas. If you remember the chapter that we talked about the entropy, I think this was chapter 4. So in chapter 4, we says in order to find entropy, so delta S of ideal gas, this is Cp ln T2 minus T1, or let's call it T out minus Tn plus R, ideal gas constant ln inlet pressure divided by outlet pressure. So this was a given equation from chapter 4. So this is what, or the first equation that we will use. Second equation, in order to find the residual entropy. So the residual entropy, this one here, will be negative the integration from 0 to the final pressure value of dV dt at constant pressure minus R over P, and all of this with respect to dP. Again, VTP, all of these terms exist in equation of state, so we can say this term from equation of state given, then we can find, so this one will be dV over dt at constant pressure, this one R over P plus AP. Okay, so if we substitute in this one, then we can say the residual entropy, so this one will be negative integration from 0 to P. Okay, R over P plus AB, AP minus R over P, and all of this with respect to dP. Again, we have two terms repeated here, so this term will be cancelled with this one, so we can say that at the end, then the residual entropy, this one will be negative integration from 0 to the final pressure of AP with respect to dP. If you did this integration, this will be minus AP square over 2. So sub in delta S equation, so substitute in delta S equation. So we have delta S, which is equal to 0, equal to negative S1R. So this one will be negative, negative will be positive A inlet pressure square over 2 plus delta S ideal gas. So this will be plus Cp ln T out over Tn plus R ln Pn over P out plus residual property 3, so this will be minus A P out square over 2. So this is the all the terms of the equation we have. So for this one, we have that the value of A, so the value of A was given to be, let me put the number. So A was 10 to the power 11. The inlet pressure, okay, let's continue. Cp, the ideal Cp, this also given was 40. The inlet temperature, this one was given 675 Kelvin. The inlet pressure was 0.5 megapascal, so converted to the SI system, so this will be 0.5 times 10 to the power 6. The outlet pressure was 0.1 megapascal, so this is 0.1 10 to the power 6. So if you check all the terms of the equations we know are, this is the ideal gas constant, 8.314. So all the terms almost there. We have A, we have inlet pressure, we have inlet temperature, inlet pressure, the value of Cp, the value of the ideal gas constant. So the only unknown in this equation will be the outlet T. So this is our only unknown. All the other parameters in this equation are known. So just we have one equation in a single unknown variable. So you can solve this equation. So again, by solving, delta S equation, then we can find that the outlet temperature, which is the variable that we need to find, will be, where is it? Okay, so the outlet temperature will be 468.8 Kelvin, and this is what we need to find.